So I'd like to begin by thanking Paul and the Physiological Society for inviting me. It's a great pleasure to be here. There are so many nice talks that I look forward to and that we've already heard, of course. So I'm going to talk about local regulation of skeletal muscle blood flow. So now we're at the local level here. And I thought I'd address first just a little bit about the characteristics of flow, and then some on the mechanisms that we know of for flow regulation. And then we'll look a bit at the effect of aerobic training. So when we talk about skeletal muscle blood flow regulation, at least during exercise, it's pretty much all about oxygen delivery to the muscle. And so if we have a person here sitting doing the one-leg knee extensor exercise in Bengt Saltin's nice model here, we have no central limitation. And we measure oxygen uptake. Of course, what we see for submaximal bout is that oxygen uptake increases to the level of the oxygen demand of the work that's being done. And what we can see, of course, also then is that flow increases accordingly to supply oxygen for that work. So if we plot leg blood flow here against workload, or if you will, oxygen demand, you see a very nice correlation between these two. It's very precisely regulated flow according to the need for oxygen. We can also see that the range of flows is quite wide. It goes here from maybe to the leg about 2.3 liters per minute up to maybe 8-9 liters per minute here. This is a wide range. And the other aspect of blood flow is that at the onset of exercise, you see, these are all data from Bengt and Per Andersen and Göran Rodegaard. You see that there is a very rapid rise. These are different exercise intensities. You see that for all of them, there's a rapid rise. So the regulation of blood flow has to sort of accommodate these three aspects of a precision, good precision here, a wide range, and a rapid change. And if we look at the overall regulation of skeletal muscle blood flow, it's all a matter of a balance between, on one hand, vasoconstriction, and on the other hand, vasodilation. Vasoconstriction is pretty much mediated by sympathetic activity, which we of course know increases during exercise. There could be some role of vasoconstrictors, but this is probably more so in disease states. The vasodilation comes about by locally formed vasodilators that act directly on the smooth muscle or via the endothelium, and then compounds that induce functional sympatholysis. And functional sympatholysis is a sort of modulation of the effect of the sympathetic activity. So it lowers the effect of the constrictive effect of the sympathetic activity. So let's look at where these vasodilators and sympathetic compounds come from in the muscle. We know they're locally formed. And there are at least three sources that we are aware of. One is the erythrocytes that you see here. The red blood cells passing through, I'll come back to this. They can release ATP and nitric oxide, vasodilators. We have endothelial cells lining the blood vessel here that also can produce nitric oxide, ATP, and prostacyclin, both to the luminal and abluminal side, to the interstitium. We have our skeletal muscle cells that can produce NO and ATP also. And anytime you have extracellular ATP, you will produce adenosine by ectonucleotidases. So what's evident is that there are several cellular sources, but as you can see, they all seem to produce the same compounds. And I'm not saying that these are the only compounds that regulate blood flow or sympatholysis, but there are some of the ones that keep popping up when people are examining blood flow regulation. Okay, so then we have to have mechanisms also that induce the release or the production of these vasodilators. And these mechanisms, there are several described. We won't go through them in detail, but just to mention some, we have mechanical signaling here, so shear stress flow mediated That's the frictional force that the blood flow exerts on the endothelium, and that leads to production of vasodilators. We have conducted vasodilation. This is an electrical coupling in the vascular wall. It can go either upstream or downstream. And this electrical coupling is very fast, goes through gap junctions. And this mechanism leads to the production of vasodilators and probably serves to coordinate flow so that any signals that are initiated at the capillaries or very small arterioles can be mediated upstream to the larger arterioles. Muscle contraction per se induces vasodilation or vasodilator production. We talked about functional sympatholysis. And then we have oxygen desaturation of the hemoglobin molecule in the erythrocytes, which I will come back to. One of the things that is quite evident when you study this is that there is a very close interaction between both the compounds and probably also these systems that allow for this precise and fast regulation of flow according to oxygen demand. And there's also redundancy so that if you have one system that's not working, another one can take over. This makes it quite complicated to study, but it probably is the key to this very nice regulation. So, I've said that it's a close coupling between oxygen need and blood flow. And the only mechanism that we have that actually can explain this coupling is this red blood cell theory. So I thought we'd look into this just briefly. This was a theory that I think in 1995 was described by Mary Ellsworth and colleagues. Has been worked on by several groups, Jose Gonzalez and Frank DiNenno, and here Ellsworth, Ellis, and Sprague have done a lot of the original work. And the theory says that when the red blood cells pass through the microvessels and the capillaries, oxygen, of course, is offloaded. This leads to probably a conformational change in the hemoglobin, causing release of the vasodilator nitric oxide, which can induce vasodilation, and release of ATP, which acts on a purinergic receptor on the endothelium, causing NO and prostaglandin formation. ATP can also be sympatholytic, so we have two ways by which ATP can induce vasodilation. So this is a very attractive theory because it then couples this oxygen release to the compounds being formed to increase flow. The problem is that we have no real direct functional evidence for this theory. It's beautiful, and hopefully at some point someone is going to be able to show this is actually functional or important functionally. Okay, so to sum up this regulation of flow and move over to training here, several vasodilators interact, allowing them for optimal regulation and compensatory mechanisms. And I mentioned here NO, prostacyclin, ATP, and adenosine to be central. There you go. Too weak in my fingers, apparently. Several vasodilator mechanisms allow for rapid and precise adjustment according to oxygen demand and for coordination of flow, which is an important aspect. And here, oxygen must be key in the precise control of blood flow in relation to metabolic demand. And what we don't know is if this erythrocyte model is the only one or if there are other oxygen sensors that could achieve this coupling. Okay, so let's look at training. And we'll start by looking at submaximal flow and what happens when you train with submaximal flow. So this is just sort of not direct data, but from a review. You see here immobilized leg, a leg that has been immobilized for 2 weeks, young active guys that have been given a plaster for a full-length cast. We have untrained and we have trained. And here you see the white here is the blood flow levels. And compared to the untrained, we see that the immobilized leg has a greater blood flow for the same submaximal work, and the trained has a lower blood flow. And we can also see that oxygen extraction here in the striped, lower for the immobilized and higher for the trained. And so one of the theories is that capillarization, increase or decrease in this case for the immobilized, capillarization can lead to an improved oxygen extraction, which then requires a lower blood flow. But this has never previously been tested because if you train, you get all sorts of changes. So we tried to do this based on the very excellent studies by Stuart Eddington and Olga Lischka and their groups. What they've done is they've taken a alpha-adrenergic receptor blocker, terazosin, giving it to rats in the drinking water, looked at the effect on capillarization, because what alpha-adrenergic receptor blockers do is that they increase blood flow, you get an increased shear stress, which we know is a stimulator for capillarization. So we tried this in healthy young men, untrained. We gave 9 of them a compound called terazosin. Every day, bedtime, they took this so that we would hopefully increase flow during the nighttime. We could see acutely that flow was increased. We took muscle biopsies before and at 2 and 4 weeks. And you see the results of capillary per fiber ratio here. You see that it increases at 4 weeks. So indeed, in humans, one of the points was here to look at whether shear stress in humans actually induces capillarization. That seemed to work. And we then, before and after this intervention, did a knee extensor exercise, graded exercise. Here you have rest. Something happened to the bar here, but you have rest, passive movement, 12 watts, 24 watts in exhaustion. You're looking at the oxygen extraction, and black bars are before and red after. And we see that oxygen extraction actually was higher after for these 3, for passive 12 watts and 24 watts. And flow was lower, significantly lower for 12 watts and 24 watts. So it seems that capillarization per se, if you get an increase, you can actually lower your flow because you get an increase in oxygen extraction. What about maximal flow then? Well, from Bengt Heltin's nice work with the knee extensor model, we know that untrained subjects have about 2.5 liters per minute and kilo of muscle. And Russ Richardson has some data here that trained individuals can have about 3.8 liters per minute and kilo, maybe slightly higher than that, but that's reaching about max. In the study by Bengt and Moritz-Sakis, we can also see that just 5 weeks of knee extensor training increases maximal flow. So I think it's pretty safe to say that endurance training will increase your capacity for flow. And now you have to remember that this is one leg knee extensor exercise. It's a limited muscle mass. We have no central limitations, and this is, of course, very important. So let's look at then if this increase in maximal flow is accompanied by a change in vasodilator capacities. Do we improve our ability to vasodilate when we train? We're looking at sensitivity to vasodilators and formation of vasodilators, prostacyclin and ATP. I've selected these 2. And then functional sympatholysis. And I will say that there is a limited amount of data on the effect of training on vasodilator systems. And the subjects that we have used have not been young elite athletes or untrained athletes. They've mostly been middle-aged. So you will see data from middle-aged. We're still alive, those of us that are middle-aged. So I think it's the system's there. Okay, so we test this by infusing then compounds into the femoral artery. In this case, a prostacyclin analog here, epoprostenol, and ATP. Epoprostenol can induce vasodilation directly by acting on smooth muscle or by interaction with NO. ATP, as you saw, acts on a receptor here, and you get NO-prostaglandin and EDHF production. And we measure then the outcome, which is vasodilation by Doppler, ultrasound Doppler. Okay, so the first study here is one that we've just completed experimental part of. This is a study on pre- and post-menopausal women, middle-aged. You see that they're pretty well matched. It's only about 4 years of age between them. It's as well as we can do in order to have the separate menopausal status. And what you're looking at here is then an infusion of this prostacyclin analog, different concentrations. Black ones here are premenopausal and white ones are postmenopausal. And it's evident that the premenopausal have a better response, better sensitivity to prostacyclin. And what about training, which is what we're interested in here? Well, if we train these women for 3 months with high-intensity spinning cycling, so intermittent high-intensity cycling, we see an improvement, overall improvement, both groups, and almost as if the postmenopausal women are acting better. They're actually getting back to the level of the premenopausal here, which is kind of interesting in just 3 months. So indeed, we can improve the sensitivity to prostacyclin. What about the production, our ability to produce prostacyclin, this vasodilator? Here we're looking at, again, middle-aged, normotensive and hypertensive men and women. We see the response. What we're doing here is we're putting microdialysis probes into the leg. We're infusing adenosine through this microdialysis probe, so into the interstitium, because we know that this is one of the pathways of vasodilation, functional vasodilation. And we're looking then at the prostacyclin response. Right? You see first that the normotensives have clearly a better response to adenosine. They produce more prostacyclin than hypertensives. And then after training, we see that the hypertensives at least can improve the formation of prostacyclin. So we can improve the formation. And if we look at the enzymes that produce prostacyclin in the muscle, we can see here, we see before training, after training, we can see that in this case, the normotensives have a higher protein level of cyclooxygenase 1 and prostacyclin synthase. There was too much variation in the hypertensives to see change, but you can see that there's sort of a tendency. So we can improve the protein levels here too. These are I'm just giving you examples. We've seen this in other studies also. This is just to give you an example of how much you can alter with training. So the prostacyclin system can be improved. What about the ATP system? Well, here we're looking at our normotensive subjects. We've trained them, and you're looking at the light blue here is the response, so the sensitivity to ATP infusion at different concentrations, light before training and dark after training. And what you see here is actually a decrease in sensitivity to ATP. So you're losing sensitivity. And this fits well with our findings on immobilization. So again, 2 weeks of full-length cast in young active individuals. And you're looking at the response in conductance to ATP or vasodilation to ATP infusion. And you see here the control leg, and you have the deconditioned leg. And here's a trained leg. So this leg has actually been trained for 5 weeks. In the final 2 weeks, we're putting a cast on the other leg. That's how they don't have 3 legs, even if they're Danes. Okay, and you can actually see that response here in the mobilized leg is greater. Trained leg, if anything, is lower. So this fits well what we saw with the decreased sensitivity during training and actually increased sensitivity with immobilization. What about production of ATP? Well, we do this again with the microdialysis technique. You're looking at interstitial ATP here. Again, control muscle, deconditioned and trained. And you see that the deconditioned muscle produces a lot less ATP during exercise. Whereas there is actually no difference here with this trained leg at least. But we have another study, and Björn Emil that Jose talked about was part of this study too, actually. And this is on active, cross-sectional, long-term active elderly men, inactive elderly men, and young men. You can see their ages here, about 65, average 23 for the young, VO2 maxes of 26, 46, and 45. So the age untrained and the young have similar VO2 max levels. They're very well trained, these age-trained group. And okay, and so if we're looking at the interstitial ATP levels here, we see that the aged, active, long, whole life active men have a greater ability to produce ATP, both here and then at 12 watts and at the relative load, which is the same for the young and the aged more or less. See that they produce more, right? So we can improve the ATP system in as much as we can increase our ability to produce ATP, but we lose our sensitivity. And if you ask me why, I think it is probably because you have so many systems, you don't have to upregulate all. You have to have very balanced regulation. This is the only interpretation I can see so far. If somebody else has a better suggestion, I'd be happy to hear. Finally here, sympatholysis. So sympatholysis, as I said, is the metabolic modulation of sympathetic activity. So you're reducing the effect of sympathetic activity. We examined this by infusing a compound called tyramine, which induces a release of noradrenaline and leading to vasoconstriction. Now, if you have a good ability for functional sympatholysis, you are able to oppose this constriction during exercise. So you will actually not lower flow or lower vasodilation when you give tyramine. Right? We have our normotensive and hypertensive subjects here. White are normotensive, gray are hypertensive. Striped bars indicate where we're infusing tyramine. This is just your exercise. This is exercise plus tyramine. Right? And what you see here in all these, 10 watts and 20 watts, all these conditions in both groups, flow is reduced, vasodilation is reduced, and this indicates that they have an impaired sympatholysis. But when we then train them for 8 weeks, what we see is that flow is no longer reduced for any of these. So training improves your ability to induce functional sympatholysis. And finally then for the inactivity, does this fit with when you are inactive? Does it go the other way? And yes, it does. We have here our casted people. Again, control your deconditioned leg and your trained leg. During exercise, remember that submaximal flow is greater in the deconditioned leg, maybe because they have less capillaries per fiber. Poor extraction, so they have to have greater flow to meet the oxygen demand. And you recall now that if you're not able to maintain flow when you infuse tyramine, you have impaired sympatholysis. And you can see that the two other legs here are doing well, but there's a reduction in flow in the deconditioned leg. So they do have impaired sympatholysis with 2 weeks of immobilization. Okay, to sum up, this effect of training on the vasodilator systems, prostacyclin system clearly improved. ATP sensitivity seems to go down. Formation of ATP goes up. Nitric oxide and adenosine, I didn't talk about the effect of training in order to not keep this too long, but we know that sensitivity to nitric oxide is more or less unaltered with training. Formation can clearly be improved. There's a lot of evidence for that. Adenosine, same as ATP, sensitivity goes down, formation is improved. And sympatholysis is improved, as we saw. All right? So the key points here, aerobic training can reduce submaximal flow, maybe because of an increased capillarization, allows for greater oxygen extraction, and enhanced maximal flow. And with training, we see an improvement in vasodilator formation and functional sympatholysis, and the opposite is seen if you're immobilizing a leg. And then finally, vasodilator sensitivity can increase or decrease depending on what compounds you're looking at with training. So with that, thank you very much.